In this video, we consider the differences in observable properties of the three most common states of matter: solids, liquids, and gases. Matter can actually exist in 5 physical states, but we're only interested in the 3 you would be most familiar with: solids, liquids, and gases. The 2 other physical states exist at the extremes of the energy spectrum. At very, very low temperatures, close to absolute zero, matter can exist as a Bose-Einstein condensate. And at very high temperatures, matter can exist as a plasma, both of which are outside the scope of our chemistry studies at this stage. The 3 states of matter we are interested in, solids, liquids, and gases, occur at intermediate temperature ranges, including the temperature ranges we encounter in our everyday experiences. Solids, liquids, and gases have different observable properties. Some of the defining observable characteristics of solids include they have a definite shape, a definite volume, and they are incompressible. Liquids, by contrast, have an indefinite shape. They conform to the shape of the container holding them. They do, however, have a definite volume, and for all intents and purposes, they are incompressible. Gases, on the other hand, have both an indefinite shape and an indefinite volume. Both their shape and their volume will conform to the shape and volume of the container which is holding that gas. And gases, as we know, are readily compressible. For example, we know that we can get a balloon full of air and readily squash it or compress it to a smaller volume. This table here shows some of the physical characteristics of solids, liquids, and gases that we've just seen, but it also provides information about the arrangement of particles, the relative distance between the particles, the relative strength of attraction between particles, and also the main modes of motion of the particles in solids, liquids, and gases. So if we look at one of the distinguishing features between solids, liquids, and gases, we see that solids have a definite rigid pattern in terms of the arrangement of particles, whereas at the other extreme, the arrangement of gas particles are quite random. Gas particles fly off in random directions, bumping into each other and bumping into the walls of the container they are kept in. The arrangement of particles in a liquid has a level of randomness to it, but the particles also typically have some sort of pattern or structure associated with them. The distance between the particles in solids is typically very close. In liquids, it's also close, but typically not as close as solids. And in gases, they are very, very far apart relative to the size of the gas particles themselves. Each particle in a gas would have a relatively long distance to travel before bumping into another gas particle or bumping into the walls of its container. The attraction between particles in solids is very, very strong, and we know this from everyday experience. If we try to pass our hand through a solid, we can't do it. So that tells us that the attraction between particles in a solid are quite strong. The attractions between particles in liquids are moderate. If we try and pass our hand through a liquid, for example by moving our hands underwater, we're able to do this with a bit of effort, indicating that there is still some significant attraction between the water particles in this liquid state. By contrast, we can move our hands through air very, very easily, indicating that the attraction between particles in gases is very, very weak by comparison. Now, the motion of particles in the 3 different states of matter is also interesting. Whilst the solids have a definite rigid pattern in terms of their arrangement of particles, they do actually vibrate somewhat around an equilibrium position. Liquids also have vibrational motion, but they also have some freedom in terms of rotational motion and a small amount of translational motion, that is, motion through space. Gases, on the other hand, have lots of motion through space, so their motion is mainly translational motion, but gas particles still vibrate and they still rotate. A couple of additional terms relating to states of matter that will be useful to know include the term fluid and the term vapor. A fluid is the collective term for liquids and gases, the 2 states of matter that readily flow. For example, you can imagine water flowing down a mountainside or natural gas flowing through gas pipelines. The term vapor refers to the gaseous state of a substance that normally exists as a liquid at room temperature and pressure. For example, water exists predominantly in the liquid state at room temperature and pressure, but we know that it exists in the gaseous state as water vapor in the atmosphere, particularly on humid days. We refer to water in the gaseous state as water vapor and not water gas. Conversely, if we think of oxygen in the atmosphere, which normally exists as a gas at room temperature and pressure, we refer to it as oxygen gas and not as oxygen vapor.